Hey everybody, this is Mr. Beckstrom, and today we are going to finally take a look at section 5.3, the fundamental theorem of calculus. So this is pretty much everything we've been building up to. So I'm going to read you part 1, although this definition from part 1 is not nearly as useful as part 2. But part 1 says that if f is continuous on the interval a to b, then the area function, which they're going to call a of x, is equal to the definite integral from little a to x of the function of t dt for all x between a and b. That is continuous on AB and differentiable on AB. The area function satisfies that the derivative of the area function is equal to the function itself. Equivalently, we have this set up here. So the derivative of the area function is equal to the derivative of the integrand or integral, which makes sense because the area function is equal to the integral. So if you take the derivative of both of them, they should be equal as well. And that means that the area function of f is an antiderivative of f on AB. All right. So this doesn't really help us solve a lot of problems here, but this next one definitely does. And this is what we're going to use in order to solve definite integrals for the rest of this class and for much of the future calculus classes if you take them. So learn this formula right here. And what this says, that if f is continuous on some interval and big F, that's the antiderivative of little f, is any antiderivative of f on AB, then the integral, the definite integral, remember definite means it has a lower and upper limit, from a to b of the function, that's the area basically under the curve and above the x-axis, or above the curve and below the x-axis, depending on what the curve is above or below the x-axis, is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. All right, so let's take a look at how we use this, because this is it. So if you need to know this, there will definitely be questions on the final exam using this. So make sure that we know it. All right, so let's take a look at this definite integral right here. So this is from 1 to 8 of 8x to the 1/3 dx. Now notice that from 1 to 8, those are all positive values. And any positive value to the 1/3 power is also going to be positive. And any positive number times the positive number is all going to be positive. So I already know that this thing is going to be completely above the x-axis. So that's not only going to give us the net area, but in this case it's also going to give us the total area, because it's not going to give us some above and some below. And another thing I could do is I could just check this function in my calculator here. And I could do that by going to y equals, and let's do 8x raised to the 1/3. And remember, we're going from 1 to 8. Let's see what that tells us. So let's change our window around a little bit. We'll go from 0 to 10. That will give us 1 to 8. And it looks like this goes pretty high. So we'll go from 0 to 100. And let's do a scale of 10 here. Let's see if we can get this in here and graph it. So it looks like from 1 right here, the area under the curve between here and 2, 3, 4, 5, 6, 7, 8 here. So that's the area that we're calculating. And remember, this is all above the x-axis, so it should all be positive. So our answer definitely should be positive. So let's see how we calculate that. Well, according to our fundamental theorem of calculus, we need to first find the antiderivative. So here we're just gonna, let's go ahead and, so that's gonna be equal to, I can pull the 8 out here, and that's gonna be x to the 1/3 from 1 to 8 dx. All right, and now I can apply the power rule. So this is equal to 8 times x, and we're going to go ahead and add 1 to 1/3, which gives us 4/3. This is the power rule for antiderivatives, all divided by 4/3, which is going to be multiplied by the reciprocal of the denominator, and we should get, let me go back a little bit. You should always put, once you take the antiderivative, instead of putting the integral there to show that it's been done, but we still need to show the limits, we usually just put a bar on the right hand side and we go from 1 to 8. So once we do the antiderivative, then we take away the integral and we just put this line on the right hand side with our limits of integration. This fraction here reduces down to 6 to the 4/3 evaluated, x to the 4/3. Let me clean that up a little bit here. A little bit too fast. 6x to the 4/3 evaluated from 1 to 8. So this is our antiderivative. So we're going to take the antiderivative evaluated at our b, which is the upper limit, minus the antiderivative evaluated a, which is the lower limit. So this is going to be 6, and then we're going to have 8 to the 4/3. So this is the function evaluated at the upper limit, minus 6, 8 to, 1, that's the lower limit, to the 4/3. And 8 to the 4/3 happens to be 16. I checked my calculator before I did the video. And 16 times 6 is 96. And this is going to be 1 to the 4/3 is 1, and 1 times 6 is 6. So this is going to be 96 minus 6, which is equal to 90. So the area under the curve, let me go back to the graph there, from here, from x equals 1 to x equals 8 is equal to 90. And that's how we use the fundamental theorem of calculus. So let's go ahead and take a look at another example here. All right, so here we have the definite integral from 0 to pi over 4. So we're in radians of 2 cosine of x dx. All right, so I want you to try to use the fundamental theorem of calculus to find the area under the curve from 0 to pi over 4. And go ahead and use your calculator to kind of check if that's going to be all above or all below the x-axis. And then when you're ready, unpause and we'll go through the solution. All right, so let's go back to the calculator here and let's do this. Let's go ahead and make sure we're in radians, which we are. We're going to change this to 2 cosine of x. And I'm actually going to change the window directly to my limits here. So I'm going to go from 0 straight to pi over 4. I'm going to show you how that's going to help us here. Pi over 4. And for the y's, let's go to like -5 to +5. So -5 to 5. And all right, take a look. See what that looks like. Okay, so this goes from 0 to pi over 4. The entire curve, once again, is completely above the x-axis, so we should have a positive area, because remember, if we have anything below the x-axis, that area is going to be negative, and it's going to cancel out some of our positive area, or all of it. And here is, so it's going from 0 to all the way over here, and it's going to be everything above the x-axis. So below the curve, 2 cosine x, and above the x-axis. That's the area that we're calculating. And I put the window so it goes directly from 0 to 4, so it'll be all the way across. All right, so let's go ahead and solve this then. So first thing I'm going to do is pull out the constant there over 4 of cosine of x dx. And now I can take the antiderivative of cosine. So since the derivative of sine is cosine, that means the antiderivative of cosine is sine. So it's going to stay positive. So this is going to end up being 2 sine of x. Remember, I'm taking the antiderivative. So now instead of writing the integral, we just write the little bar on the right. And, you know, I never knew what that bar was called. Somebody let me know what that bar is called. Maybe I'll give you some extra credit here. And we're going to go from 0 to pi over 4. And this is going to equal, using this notation here, so it's the antiderivative. So 2 sine of the upper limit, which is pi over 4, minus 2 sine of the lower limit, which is 0. So that's going to be equal to, well, the sine of pi over 4 is 1. 1 times 2 is 2, so this is going to be 2 minus the sine of 0 is 0. So we get an answer of 2. Now, if I had accidentally taken the wrong sign here, and I thought the antiderivative was negative sine of x, because that's like a bit of stuff that gets confused all the time, then my answer would have come out negative 2. And then I would have looked at my my graph here and said, wait, I should get a positive number, so I did something wrong. So that's kind of one way to check. All right, let's take a look at another example here. All right, so here we have from 0 to natural log of 8 of e to the x dx. So once again, I'm going to go to my window here, and let's go from 0 to, and we're going to do natural log. That's a natural log of 8 here. It'll give us a decimal approximation. And we're going, that's our x values. Keep the y values the same. Let's see if it comes out okay. And it does. So look at this. Notice that we're going to have some positive value and some negative value here. So this answer here is not going to give us the total area. It's going to give us the net area. So it's going to give us the area up here minus the area down here. So it's not going to actually tell us specifically how much area is above and how much area is below. It's just going to give us what the difference is. So if we want to find the total area, then we would have to actually divide this into 2 integrals. And let's go ahead and possibly do that after this one, just to see what the total area is. But right now we're going to find the area. That's the net area. That's the area above the x-axis minus the area below the x-axis. So this is going to be, let me just make sure. Oh, wait. I didn't even put the function in there. Man, I should delete all this out. But that was weird. I was like, nah, that doesn't seem right there. Okay, we actually have to put the function in, don't we? Okay. So somebody get on me for that, because I am losing my mind. All right, let's try it again here. I think we're going to have to go a little bit higher on our window for our y values. Let's go to 15, see if that does it for us. And it does. So once again, all of it is above the x-axis here. So we should just be getting a positive area. Sorry about that. I forgot to do that. All right. And it's the area from here to here, all above between the x-axis and this function here, the function e to the x. Yeah, man, last one didn't look right. All right, so this is going to be equal to the antiderivative of e to the x is e to the x, because the derivative of e to the x is e to the x. So this is going to end up being just e to the x, evaluated from 0 to the natural log of 8. So that's equal to e to the natural log of 8 minus e to the 0. And that's going to be e natural log of 8. E and natural log are the inverse functions of each other, so they cancel out. So we're just left with 8 minus e to the 0 is 1. I believe, I haven't done e to the 0 in forever, but I'm 99.9% sure that's equal to 1. Yep. 8 minus 1, so we get a total of 7. So the area above between the curve and the function e to the x from 0 to natural log of 8 is equal to 7. Okay, last one. Now we're going to take a look at secant squared of theta from 0 to pi over 4. So first thing I want to do is put this in my calculator here. So I'm going to go to the function here. Remember, secant is 1 over cosine. So I can write this as 1 over divided by cosine of x and then squared. So this is the same thing as secant squared of theta. And then I'm going to set my window from 0 to pi over 4. So second pi over 4. Kind of get an idea of what I'm taking a look at here. Go to the graph, and I need to definitely change my y. So let's go from -5 to +5 here. And take a look again. That's a little bit better. So it's all, again, above the x-axis here, so we're going to get just a positive area. And it's from 0 to pi over 4. All right, now if I were to draw a rectangle here, here it has a height of 1, and there it looks like it has a height of 2, right? And then the length here is pi over 4. Let's see what pi over 4. So if I just did like 1.5 times about 0.78, let's see what I get. So 1.5, which is about the average height of this thing, times the width, which is, well, I'll put in pi over 4. Divided by 4. This kind of gives me an estimate of kind of what I'm looking for. So I'm looking for some value that's around 1, positive 1, right? Maybe a little bit over positive 1. And this is going to help in case I get something that's just way crazy. All right. So let's go ahead and take a look at this then. So this is, well, if the derivative of tangent is secant squared, then the antiderivative of secant squared is tangent. So this is going to be the tangent of theta evaluated from 0 to pi over 4. All right, and that's going to be equal to the tangent of pi over 4 minus the tangent of 0, right? And that's going to be equal to the tangent of pi over 4. Well, that's the same thing as the sine of pi over 4 over the cosine of pi over 4, which is going to be root 2 over 2 divided by root 2 over 2, which is just 1. And then the tangent of 0 is the sine of 0 over the cosine of 0, which is just 0. So I get an answer of positive 1. And that looks like it's pretty close to what I thought it might be close to there. So this just gives me a rough estimate if I want to take like a rectangle and kind of get an idea of what kind of area I'm going to look at. All right, guys. I hope this helps. If you have any questions, please let me know. And I hope you have a great rest of your weekend. Thanks.